Hi guys, I'm Carl,
I'm Peter.
and we have the solar tracker. And the basic premise is that this is a device that will track the sun. So the basic requirements for this is that we want the servo to control the angle of a solar panel, and we're going to try and maximize the output of the power output of that solar panel. And we're using that by tracking light sources and changing the angle accordingly. And then we have an LCD that monitors the voltage of the solar panel.
And then some of our specifications that we all know that we can test is that the servo plane will level out when each photocell has the same voltage. So if you want to test it out, you apply a multimeter to each side, you can see it level out. Both of them are the same. And the output of the panel, which you can attach the multimeter to the output of the solar panel, and you can verify it with LCD when you get the multimeter. And then go into our hard block or system block diagram. For our hardware design, it's 3 inputs, 2 photocells, and a solar panel. That'll go into our Arduino, and then it'll output the LCD, and it will control the servo. And for the software design, we start off by initializing everything, and then from there, the mini photocells will take in the voltage readings, and from there, it will output that to the ADC, and then it'll go into a voltage check, which will keep looping back. But with the voltage check, it will compare the 2 voltages at each photocell, and based on the statement, it will move and fluctuate and have an output to the servo, which will move it. And then from there, it will also output to the LCD, and with the LCD, the solar panel reading is also going into the LCD, which will verify and output the maximum output power. And from there, we go into like a timeout, where we have a counter that will keep counting out for each loop, and once it reaches a variable for which we call timeout, it will keep verifying and keep moving, so you can adjust that variable. So if you want it quick, you can just have it check for a couple seconds, or you can have it check for a minute or so, depending on what you put. And it'll keep going through and getting the light readings.
Yeah, once it times out though, it'll stop, because it's assuming that they might not be able to get an equal balance for both of the solar cells, and you probably don't want it just like going back and forth between 2 very close states. So we have a timeout. If you push a button, it resets the whole thing, so you can start it over.
On the solar power, did you use, what are you using to calculate that, measure that?
We use the same basic formula from the ADC tutorial, because we're just using voltage.
Are you just using voltage?
For
Okay,
now,
so it's not
yeah.
power per se?
Yeah, it's not power per se, it's the open circuit voltage.
You were going to have power buttons.
We ran into some issues with power. Some of the readings got a little strange, so for now we just did voltage. So some things that were kind of difficult and parts of our hardware and software design that were interesting. The solar panel, fairly straightforward, but the servo, we used a full rotational servo, and a lot of people use the angular ones. So we wanted to try the full rotational one. The difference is on the angular ones, you put in a pulse width and it like changes it, puts it to an angle. The full rotational one, you put in a pulse width and it just rotates it in a direction. So it's a little bit different. It turns out, I think it uses a little bit less power too, but it was an interesting design decision. I think the angular one might have been a little bit easier, but the full rotational one, it works fine.
Yeah, and for that full rotational servo, the interesting thing is rather than using voltage, and if you increase the voltage, you'll move one way, not you use pulse width, which I thought was interesting, which we learned from Harris when we talked to him, that use pulse width rather than frequency or voltage, and it would move depending on that. So like with our rotational, you'll see it, once it gets to a level plane, it'll keep like leveling out, because it'll keep checking it. The only way we can do it is to push one way rather than just going to a certain angle. As an angular 5 as the serial number, and the 2 photocells along with an LCD that will output it. In the software design, we had ADC and we used much of
Status of the project, we had a lot of difficulty getting the servo to work for a while, which put us significantly behind where we wanted to be. So things like the voltage reading, we would rather have that be power, but that gave us a new set of challenges. But also designing it in that box was a little bit of a nightmare too, because it's really small. But the basic functionality is all there. It will effectively track the light. And it's also fairly precise. Sometimes it gets a little weird if there's light coming from like the side, because it only angles in one axis of rotation. So sometimes if you have a light source that's kind of at a weird angle, hitting one of the sensors can cause it to be a little bit stupid.
In this room, we have a whole bunch of lights around, so it's tough to really show. So that's why when we test it, we'll turn off the lights, so it'll be easier. And it'll most likely just track to the outside light, so in the sun it would work a lot better.
And light fluctuations also cause a great deal of headache when trying to test it, especially working in a room with other people working. Sometimes the light changes quite dramatically, which can be funny because sometimes we were working in a lab and the light would go out and I'd watch my thing angle to the nearest light. That was cool. But it was also really frustrating to test it sometimes. When you're trying to look really close and you realize your shadow is causing a nightmare. The solar panel, and if there's light coming from, say, over here, it'll hit this one, but not this one. So in the software, it does a comparison between the 2 voltage levels, and then whichever one is higher, it'll rotate in that direction. So again, if the light was here, it's going to want to rotate that way, and then it'll check again. And then at that point, this light will be a little bit brighter, but still this one will probably be greater, so it'll turn again. So it's actually a lot simpler than our sensor project because the user doesn't really care how many lumens each one is getting. It really only matters if it's angling the right way. So we basically just compare raw numbers. We didn't have to do any conversions to lux or anything.
Then we press the reset button, it'll start the cycle. We'll start searching. So follow the source.
Yeah, and sometimes, as you can see, like if you angle the light wrong, it'll still go the wrong way. Because when you're using like a concentrated thing like a flashlight, it's a little bit different than like ambient light.
Yeah.
But it tracks rather well.
On the sun.
Yeah. So like if we, once it finds it works better with bigger light sources like the sun or switches up here. It doesn't really work well with lights, probably due to just the cheap photocells that we got. But you just keep pressing that. You can try to battle the sun over there. And with the thing with flashlight, you have to make sure it hits both lights.
Yeah, so if you just flash your light on one of them, like you're gonna cause it to do exactly that. So
Just keep rotating.
yeah, it'll just keep rotating in that direction.
And yeah, and it'll show out here. So right now it's outputting at maximum 5 volts. With it on, you can cover it up, and it'll go down. But since there's a lot of light in here, it shows close to between 4 to 5 volts. And that's it.
Cool.